Welcome. Today in this lecture we will discuss about lattice vibration in solids. So here we will study what is lattice vibration, and simply we will find out some nature of lattice vibration, frequency, like this. So firstly, lattice vibration. So we know crystal consists of lattice, regular, periodic arrangement of points, and if we add atoms or motifs, then we get crystal structure. This we already know. So crystal will consist of lattice points, and in this we will place the atoms. Now we can consider that these atoms are bonded to each other. Atoms are bonded to each other or connected to each other by some elastic spring, which we called as massless. So how we consider the lattice? Like say we have lattice points and we consider atoms in these lattice points, and they are connected by some form of elastic massless spring. So what is the implication? এরকম ধরলে কি হবে? So this will means that the vibration of an atom, or when an atom vibrates, is shared by other connected atoms. So here energy is shared or transferred to other atoms also due to this connection by a spring. So each atom is connected to the other neighboring atom, so there will be transfer of energy. So we call this as coupled vibration, or this is similar to the coupled oscillation. So here what will happen, if a atom vibrates, so neighboring atoms will also vibrate. So here we see we will consider the vibration of the entire lattice rather than single lattice, which we call as lattice vibration. So what is this lattice vibration? So all atoms are connected or coupled to other atoms. So whenever an atom vibrates in lattice points, the other atoms in the other lattice points also vibrate. So we consider the vibration of the entire lattice. So this is lattice vibration. So বুঝা গেছে lattice vibration মানে একটা অ্যাটম ভাইব্রেট হলে নিয়ার বাই অ্যাটমগুলো ভাইব্রেট হবে এবং সবগুলো। সো এখানে আমরা বলবো পুরো ল্যাটিসটাই ভাইব্রেট হচ্ছে। সো দিস ইজ ল্যাটিস ভাইব্রেশন। সো দেয়ার মে বি টু টাইপ অফ ল্যাটিস ভাইব্রেশন। ওয়ান ইজ the vibration due to own internal energy of the atoms. অ্যাটমগুলো নিজেরা তার ইকুইলিব্রিয়াম পজিশনের রেফারেন্সে they can vibrate. Atoms can vibrate, internal atom they can vibrate freely, which we called normal modes. This is basically due to thermal energy, and we will here get thermal properties due to this such type of vibration, that is like say specific heat, thermal conductivity. So thermal vibration এর জন্য যেটা হবে, অ্যাটমগুলো তার মিন পজিশনে একটু ভাইব্রেট হবে তার ইন্টারনাল এনার্জির জন্য, বেসিক্যালি ডিউ টু থার্মাল এনার্জি। তারপরে আমরা যে প্রপার্টিগুলো যেগুলো স্টাডি করতে পারবো, স্পেসিফিক হিট, থার্মাল কন্ডাক্টিভিটি এটসেট্রা। আরেকটা হতে পারে ডিউ টু এক্সটার্নাল অর ডাইনামিক্যাল ফোর্সেস। এক্সটার্নাল কোনো ফোর্স যদি দেই, যেমন ধরো আমরা যদি ইফ উই গিভ মেকানিক্যাল ফোর্স, ইট উইল গিভ রাইজ টু অ্যাকোস্টিক প্রপার্টিস অফ দ্য সলিডস। একটা হতে পারে ইলেকট্রোম্যাগনেটিক ফোর্স যদি দেই, দ্যাট উইল গিভ রাইজ টু অপটিক্যাল প্রপার্টিস। সো it was just idea of lattice vibration. So lattice will vibrate as a whole due to vibration of individual atoms, as all atoms are connected or coupled. So this is a coupled vibration. So there may be normal mode vibration which give rise to thermal properties due to internal energy, which is specifically thermal conductivity, etc. And there may be external forces, which is like mechanical, which will give rise to acoustic property. There may be electromagnetic, which give rise to optical properties. So, okay. So now we will simply study a simplified case of one-dimensional monoatomic lattice, where we consider one-dimensional chain and each atom is connected to other atom in a one-dimensional fashion. So we will study how the vibration occurs, and here we will take the vibration of the wave that passes through this one-dimensional lattice and find out the angular frequency and other parameters. So we consider one-dimensional monoatomic lattice vibration. Here we consider the vibration of the wave passes through a one-dimensional chain and how it behaves like this. So here we consider one-dimensional monoatomic chain of each atom mass m. Here consider same type of atom, monoatomic. A is the interatomic separation at the equilibrium position. Here you consider chain of monoatomic lattice where atoms are connected to each other by massless elastic spring. This is important. Here what we consider for simplification, we consider one-dimensional chain. So here we consider one-dimensional chain of monoatomic lattice, each of mass m, and they are connected by some massless springs. Okay, their spring constant we consider as beta, and we okay, interatomic separation is A and each atom mass is A. So this assumption we consider, and we consider the vibration passing through this one-dimensional chain. Okay. Now second assumption is we consider only nearest neighbor interaction. So obviously, as this is a one-dimensional chain, each atom will interact with two atoms. We consider left and right side. So each atom will interact with its neighboring sides. So we consider the vibration of the lattice or the wave that passing, the vibrational wave that is passing through the lattice, giving us some type of force, due to some type of force, obeying Hooke's law. Hooke's law is force proportional to displacement, the restoring force. Here we consider an elastic spring. So we consider here harmonic approximation. So if due to this vibration or the wave that passing through the crystals, the atoms will be displaced, and this displacement will be proportional to the restoring force. So here we consider a harmonic approximation. Okay. Now another approximation is when the elastic wave, here we call these waves as elastic wave as passing through the waves. Here we consider elastic vibrations connected by springs. So elastic wave, as it passes through the crystal, okay, atoms may vibrate in parallel or perpendicular direction to the wave propagation. So if wave propagates along positive x direction, it may vibrate perpendicularly, that is the transverse vibration or longitudinal vibration, but we consider only longitudinal vibration along propagation. So this is our assumption. So we consider vibration that atom vibrates longitudinally. So we consider only x direction. It may be along positive x or negative x direction propagation. So these are the few basic assumptions on which we will derive the frequency of the elastic wave due to vibration of the lattice atoms. So here we consider again the picture that one-dimensional mass points, okay, mass, all are same mass, so they are connected by elastic spring or spring constant beta, and interatomic separation is A. Okay, so now we consider any reference atom as nth atom, and the forward direction we take n plus 1, n plus 2 like this. এখানে আমরা নাম্বারিংটা কিভাবে করব, যে কোনো একটা রেফারেন্সকে n ধরে নেব আর তার পজিটিভ এক্স ডিরেকশনে যেগুলো থাকবে n plus 1 নাম্বার atom n plus 2, আর পেছনে যেগুলো থাকবে ব্যাকওয়ার্ড ডিরেকশন এগুলো n minus 1, n minus 2 এভাবে নাম্বারিং করব। ওকে, সো nth atom will interact with n plus 1 and n minus 1. Similarly n minus 1 will interact with nth and n minus 2, এখানে আমরা শুধু নাইবারিং ইন্টারাকশন করব। ঠিক আছে, দিস ইজ দ্য ইকুইলিব্রিয়াম পজিশন, মানে original position যেটা ছিল। Now say a wave passes or due to vibration the equilibrium position is displaced, so this will obviously be displaced. Say it is displaced here, it is displaced here, it is displaced here, so like this. So এখানে কি হবে, ইকুইলিব্রিয়াম পজিশন থেকে nth atomটা এখানে চলে আসবে, n plus 1টা এখানে, n minus 1টা এখানে। ওকে, সো অরিজিনালি এটা এখানে ছিল, এটা ডিসপ্লেস হয়ে গেল। ঠিক আছে, so a displacement from equilibrium position we consider as x. So for nth atom displacement is x n, so we consider this as x n plus 1 and this is x n minus 1. So এখানে simple equilibrium position, so it is displaced position. Okay, this is original position, displaced position. Now we apply Hooke's law, so we know force is minus beta x. Do you remember this? So here this will interact with this, this will interact with this, so net force on nth atom, so we consider the force on nth atom minus xn minus xn plus 1, the net displacement is this, so beta into this, and due to these two atoms there will be force between these two pair, so this will be minus beta xn minus 1, this is the net displacement due to this. Here you see this is the reference, so this will be at the first position, the reference, the displacement of nth atom, so whichever reference you take, this will be in the first position. Okay, so now we use Newton's law, so this equal to beta xn plus 1 plus xn minus 1 minus 2xn, you can directly write this, so this is one of the equation, we give it equation number 1. Okay, now we consider this elastic wave passing through the solid, so we consider a plane traveling wave solution passing through the crystal or the lattice of the form xn equal to a e to the power I omega t minus k n a. So this is the traveling wave solution, a is the amplitude, omega is the angular frequency, 2 pi nu, k is the wave vector, this 2 pi by lambda. So here we consider wave solution where same frequency is considered same for the wave, amplitude is same, and here only the phase change, the phase part will be given by this, so phase part is different for different atoms, so this will be given by this k n a factor. So for nth atom it will be given by Na, for n plus 1th atom it will be written as n plus 1a, and for xn minus 1 it will be written as a I omega t minus k n minus 1a. So this type of solution 2 1 2 2 2 3, this type of solutions are called normal modes solution. These are simple solution, simplest solution, so normal mode solution, and we take of the form complex solutions, so these are very easy to solve because these are exponential part. So once we substitute, now we will substitute 2 in 1, so substituting this, all exponential term will get cancelled out and we will have some simple expression. From this we will find omega, this is the angular frequency of the elastic wave due to lattice vibration. So once you substitute the values that we've shown, earlier, that is, we substitute, if you substitute like say these solutions in equation 1, left side you will get minus m omega square, here you will find minus omega square. So simply you substitute, you will find the solution as minus m omega square, this will be left side, equal to beta e to the power I k a minus e to the power minus I k a minus 2 plus e to the power I k a. So this we can further simplify it like this, I k a by 2 minus e to the power minus I k a by 2. This is simple, whole square. So this a square will be this, b square will be this, minus 12 will be this. You substitute. Now you remember the trigonometric formula, sin x will be e to the power ix minus e to the power minus ix by 2i. So sin square x will be minus 1 by 4 to the power ix minus e to the power minus ix whole square. Now this and these are very similar. If you take x equal to ka by 2, so you substitute, you will find it minus 4 beta sin square x or sin square ka by 2. So minus m omega square. So you substitute, so omega square will be 4 beta by m sin square k by 2, or omega will be plus minus root over 4 beta by m sin k by 2. You can also take mod of this. So sin square k by 2. So this is our expression. Now as frequency should be positive, we neglect the negative components and omega will be given by root 4 beta by m sin k by 2. Okay. So this is our expression for, so this is equation 3. See, this is our expression for regular frequency of the elastic wave that is passing through the crystals and resultant due to lattice vibration, caused by the lattice vibration. So you can also take 2 out, so it will be 2 root beta by m sin k by 2. Okay. So here we see that this omega, it depends on the wave vector. So omega depends on k. So this relation, omega versus k relation, is called as, very important, you should remember, it is dispersion relation. Very similar to the dispersion of light wave by a medium where frequency is dependent on the refractive index. So dispersion relation and omega versus k plot, we call it dispersion curve. Okay. So here we get the expression of dispersion relation and dispersion curve. Now we will plot this dispersion relation. Okay. Now we have the relation omega equal to 2 root beta by m sin k by 2, or omega 0 sin k by 2. We can write like this. Omega 0 is this part, the fixed frequency part. Now how it will look like if you plot omega versus k? Here it is omega, here it is k. So you see sin k by 2 is less than or equal to 1. Its maximum value will be 1. If you take mod of this, plus and minus 1, so maximum value of omega will be, there will be some limiting value. So omega maximum value, it may be omega 0 plus minus. Okay. So here we have limiting value. So at k equal to 0, so sin theta we know it is sinusoidal, so it will be like this. So it will be like this, it will be like this. So it will be maximum value is plus omega 0, it will be minus omega 0. Omega 0 means not minus, magnitude it will be positive. So this, okay. So this is the dispersion curve. Now first, when will be the first maxima will occur? First maximum will occur, you know, sin k by 2, you can take it at 1, or k value may be plus minus n pi by a. We know this. So n is odd. If n is odd, then we will have this equal to 1. Otherwise it will be 0. So n may be So k value may be plus minus pi by a, plus minus 3 pi by a, like this. So first maxima will be, first maxima boundary would be minus pi by a to plus pi by a. So this is minus pi by a, this is plus pi by a. So this range of k is called first Brillouin zone. So first Brillouin zone is the value of k lying between minus pi by 2 plus pi by a. So at minus pi by a you have a maximum value, at plus pi by a you have maximum value, and in between this you have an increasing value. So this is frequency dependent wave vector. Okay, so this is changing. So this is the dispersion curve. Now here we introduce two terms. Simply you remember the phase velocity. So what is the phase velocity? If you have multiple waves superposed, so the velocity of each of the constituent wave, a particular point or particular phase of constituent wave, so it is velocity of constituent wave or advancement of a point of constant phase of any particular wave along the direction of propagation. Direction of propagation. So you have multiple waves, they have their individual velocity, that is the phase velocity, and they superpose to give you a resultant wave. So okay, so this we denote by phase. Now you also have group velocity. So group velocity means the advancement of resultant wave actually transfers energy. So it is an envelope. Okay, this is the group velocity. This is the resultant velocity with which the wave moves. This group velocity actually determines the velocity in the medium, which carries the sound energy, So phase velocity. So this resultant wave packet, this wave packet will move with a constant velocity, which will cause group velocity, and inside this we will have constituent wave which have phase velocity. They may be different, they may be same. Okay, so phase velocity is written by omega by k, numerical value, and group velocity is written as d omega dk. Okay, so how can we write phase velocity omega by k from this expression? So if we write omega by k, it will be 2 by k root beta by m sin ka by 2. Now we can do some tricks. We take 2 in the numerator, ka by 2, and multiply by a. So we can write it ka by 2. This is same as this, root beta by m sin ka by 2. So this we write a root beta by m sin ka by 2 by ka by 2. We take it into a beautiful form. You can take also mod a k by 2 minus sin theta by theta, a format of the energy. Yes, this is same. This is one of the relation. And how group velocity? Group velocity, you simply differentiate this. So it will be 2 root beta by m cos ka by 2 into a by 2. So this 2 will get cancelled. So it will be a root beta m by 2 cos ka by 2. So this is group velocity. Okay. So this is group and this is phase. Okay. So phase velocity is individual constituent velocity. Okay. And group velocity. You simply differentiate. You will get this. You simply differentiate this. You will get this. So simply you put so you have phase velocity, we have group velocity. So there will be two type of velocity, because there will be multiple wave, defined vibrational wave. So this will result, this will superpose, and we will have a resultant wave which moves through the wave. That is the actual elastic wave that is passing through the crystal, so that will have a group velocity. So we will study the individual phase velocity and group velocity. We will find out in the next slide the value for different cases. Okay, now we study three scenarios. We have the formula, you know, omega is 2 root beta by m sine k by 2. We can also take mod of this because we are taking the positive values only. Then we have phase velocity, that is a root beta by m mod of sine k by 2 by k by 2. And we have group velocity, that is a root beta by m cos k by 2. Okay, so we have already these three relations, and dispersion curve also we have studied. Okay, so now in the first scenario, if low frequency or wavelength very high, means very greater than a, in that scenario k is 2 pi by lambda, so this will tends to 0 or very small. So if this is very small, we know sine theta by theta will tends to 1. So what will be the phase velocity? Phase velocity will be a root beta by m. What will be group velocity? Cos theta will tends to 1. If this k tends to 0, cos theta tends to 1. So obviously this also beta by m. So both, so interesting result is phase velocity is equal to group velocity. So here we don't have any dispersion. So how the situation? So this is case of homogeneous media. There is no effect of atomic structure on the elastic wave propagation. So here we consider continuous step. So how the wave, how the solid will look like to the wave, propagating wave, it will look like continuous. So this is the wavelength, say this is the wavelength of the propagating wave. So these are the interatomic separation. So you see interatomic separation is very small, will appear very small to the elastic wave that is passing through the wave. So it will appear as a solid medium to the wave. Okay, so this is the one of the case. Now second case is the very high frequency. Very high frequency, in this case k will be large, so here we will have dispersion. Obviously here we will have phase velocity, group velocity. This is a general case. In case of higher frequency, okay, so we will have phase velocity this, group velocity this. Now third case is when omega equal to 2 beta by m. When this will happen? When sine k by 2 equal to 1. This already we have discussed in the earlier slide. So k will have value plus minus n pi by a. So n will be odd, it will be maximum when n is even, and if n is even, it is minimum. So here we have particular boundary here where this frequency is maximum. So what happens, you see there is some limit of frequency of propagation. So maximum frequency is 2 root beta by m. Okay, so this acts like a low pass filter. This is important. This term is used in electronics. Low pass filter means it allows only up to certain frequency from 0 to omega 0. 0 to omega 0, E of the maximum, E of the allowed হবে 0 থেকে একটা সার্টেন ফ্রিকোয়েন্সি অবধি অ্যালাউড হবে, মানে লোয়ার রেঞ্জে অ্যালাউড হবে, তার বেশি গেলে কাট অফ হয়ে যাবে বা ফ্রিকোয়েন্সিটা ট্রাভেল করতে পারবে না। সো এটা ইন্টারেস্টিং একটা ফেনোমেনা এখানে আমরা পাচ্ছি লো পাস ফিল্টার, ঠিক আছে। ওকে, সো নাও ইফ ইউ টেক n equal to 1, then k a by 2 equal to pi by a not this, in that case k will be 2 pi by lambda equal to pi by a, or we will get lambda equal to, wavelength will be equal to 2 times of a. This is important. So when k is pi a or plus minus pi by a, you see there is a maximum occurs and lambda is 2a. Now from Bragg's law of X-ray diffraction also we get 2d sin theta equal to n lambda. Now if theta is 90 means normal incidence, n equal to 1. Here also we get lambda equal to 2d. So these two are very similar relations. So this is Bragg's reflection. So when this condition is satisfied, what happens? There occurs reflection of the incident wave. Here also you see when lambda is equal to 2a, there occurs some maximum values of vibration frequency, maximum frequency allowed. So this gives rise to phenomena of standing wave. Okay, this is Bragg reflection, this is standing wave. So these are very similar. So why this is called standing wave? Now you see in this scenario, what will be the phase velocity? Phase velocity will be 2 root beta by m. Obviously this will be this sin theta will be 1, so it will be 1 by k by 2. You can take this or whatever this value. Okay, so a beta by m 1 by k by 2. Okay, so this you get cancel, and so it will be 2 by k root beta by m. This is the normal part, phase velocity. But what is interesting is group velocity. Now you see when this n k is pi by a, so obviously k is pi by a, this is 0, so group velocity is 0. So no transfer of energy take place. No transfer of energy take place because the group velocity actually carries the energy still. So there no energy is carried, so that is it is called standing waves. Okay, so this is the 3 scenario. So you should remember. So what is lattice vibration? Vibration, coupled vibration of the entire lattice. That is the lattice vibration. From this we consider one-dimensional lattice, monoatomic lattice. From this we find the frequency of this. We find the phase velocity, group velocity. There are 3 scenarios. So this is the introductory part to the lattice vibration, and this will be sufficient for this our syllabus. So next topic we will be studying about the phonons, water phonons, a very brief introductions, and some indirect experimental observation of phonon existence. Actually phonon is very similar to that analogy to the photon in case of electromagnetic radiation. So we will be studying it in the next class. Thank you.